won't have a fire drill if it's raining. No. And even more exciting is we're going to have our test on Wednesday. There will be a help session today at what? 3 o'clock in this room. So that's different from our normal room. It's in this room at 3 o'clock. We won't have our normal Thursday session because we'll just finish up our exam. But we'll have it today at 3 o'clock in this room. And I'll record it if you're not able to make it. I know a lot of you are going to have it various times. So I'll record it and put it online. I'm also going to record this class. We'll do some review here. I sent out a message earlier with a little 5-minute YouTube clip just sort of reviewing what's all going to be on that test. There will be an extra credit question. Yeah, I know. That's the first time. But you have to get the answer right. All right? Like you have to get the correct number because I'm not going to get partial credit or anything. And it's a question that I felt, I put it on the test and it's like, I don't know, this question's kind of hard. And it's not really that hard. Like I could have left it on the test, but I thought, no, I'll just give it as extra credit. Nice guy, right? Yeah. But the test is difficult, so it's difficult material. So make sure that you're prepared. I'm a little bit nervous about it. Are y'all a little bit nervous about it?
Yeah.
Yeah.
I'm worried about showing up at the wrong place. Where is it again?
It's in Telch Auditorium.
Same thing?
At our normal time. All right. We just sort of have a few loose ends to tidy up, and so let's do that. We didn't do this quick test question, so let's do it. It's on page 121. Consider this figure. What is the normal force acting on the block? Hopefully you don't have to really think about this very much at this point. You can just tell me, boom, it's this. It looks like I used 9.8 for G on this, so your weight is going to be 98 newtons. What is the normal force? All right, feel free to ask your neighbor if you like. What's that? All right, I'm going to stop at 135. 135. All right, guys, hopefully at this time you can just look at this and say the normal force is the y component of the weight, which is the weight times the sine of 60, right? Because we know that we're always going to have those forces. So if I have my coordinate system here, I have my forces. Remember, I'm going to have the y component of the weight, that's Fwy, and the y component of the weight is equal to Fw times the sine of 60. Fw, I said in this case I use 9.8, so it's going to be 98 newtons times the sine of 60, which is 85. So A is the right answer. If you put C, if you put C, which is not correct, some of you put C, that's because instead of sine of 60, you probably did sine of 30 is probably what you did. So don't forget that we have this this force weight vector right here, that we always want to use this angle. So make sure that you always take 90 minus the incline angle. If you put 98, which some of you did, that's also not correct. What you did is you said that the normal force is equal to the weight. On an inclined plane, the normal force will be less than the weight, because the normal force will just be a component of the weight, the y component of the weight. All right? We could, just to sort of finish out the vector diagram here, I have Fwx, which is Fw cosine of 60, and then I have the normal force, and there's no friction in this. So my normal force is the y component. If I wanted to know the acceleration, I would just say, well, the force in the x direction is Fw cosine of 60, and that's going to equal to the mass times the acceleration in the x direction. All right, so if I wanted to know the acceleration, which you could ask, that's how I'd find it. Let's see, I can finish this off. It's just 10 times g cosine 60 equals 10 times a. The 10's cancel. I'm left with a equals g cosine 60, which is 5 meters per second squared. All right. You should know the inclined plane problem. There'll be, several problems on the test about that. Let's see, I think I have one more here. In the figure, what is the coefficient of static friction between the block and the inclined plane required to keep the block in place? What is the coefficient of static friction required to keep the block in place? All right, let's do about 15 more seconds, 10 minutes, maybe 10 seconds. We'll go to 140, 140. I'm going to stop. Mostly put A, I think that's right, but I'm going to go ahead and mark it and then we'll check. So going back to that figure, I have this inclined plane. I know that my static friction acts in this direction, and if it's static, that means that it has to be equal to the force that's in this direction. That's going to be Fwx, and so Fwx, or rather the sum of the forces in the x direction, equals 0 because it's static. That's going to be Fwx minus Fs equals 0. So Fs will equal Fwx, which is going to be Fw times the cosine of, what was that angle? Right, the angle of the incline is 30, so this is going to be cosine of 60. That's 98 times cosine of 60, which is 49 newtons. That's taking this to be 98 newtons. Okay, so if that's my static frictional force, I know what the normal force is from this one. Then I can find mu. Mu is just going to be the static frictional force divided by the normal force. It's going to be 49 over 85. Is that 0.6? It is 0.6. So A is the right answer. Yeah. All right. Okay. All right. Have a few more clicker questions from the concept test for Chapter 4 and Chapter 5, and then I'll spend a little bit of time just sort of reviewing over what to expect. See, we did this one correct. There were just a couple at the end. I gave y'all the answer, but I didn't really go over it, right? Did I go over this one? About the tires? Okay. And this one, right, the cart, yeah, okay, a box of weight 100 newtons is at rest on a floor where mu s is 0.5. I've already given you the answer here, right? So I'm not going to do the clicker question. Oh, come on. A box of weight 100 newtons is at rest on a floor where mu s is 0.5. A rope is attached to the box and pulled horizontally. Which way does the box move? Okay, so here I know that the weight is 100 newtons. Hey, y'all like the white background? Is that better? It took me like 30 seconds to do it. I don't know why I've been putting this off for 10 years to do it. Okay, so I know then that the normal force is also 100 newtons. The normal force is 100 newtons because it's on a flat surface, so the normal force will equal the weight. So the normal force is 100 newtons. Then I can also calculate what the static friction is. The maximum static friction is going to be mu s times the normal force. That's 0.5 times the normal force, which is 100 newtons. So the maximum static friction is 50 newtons. However, I'm only applying 30 newtons of force. So if I pull on this thing with 30 newtons of force, and I have a maximum static friction of 50 newtons, what's going to happen to the block? It doesn't move at all, right? What is my static frictional force? That's tricky. What is the static frictional force?
30.
It's 30 newtons. It's not 50 newtons. That's my maximum value. Remember that frictional force can have a range all the way up to the maximum value? If I pull on this direction with 30 newtons, I get 30 newtons in the opposite direction from the static frictional force. So in this opposite direction, I get a frictional force of 30 newtons. Okay? And here a box sits on a flat board. If you lift one end of the board, making an angle with the floor. As you increase the angle, the box will eventually begin to slide down. So I have some things that are happening here. The component of the gravity force parallel to the plane increases. Is that true? F of x does increase. In fact, if I have this block, you can think about F of x as the force of the weight along this axis. If I increase this all the way up to 90 degrees, then F of x is equal to the weight. There is no y component. There's only the x component. All right, so this is the correct answer. This does not change. The coefficient of static friction does not change. That's dependent upon the surfaces, and the surfaces don't change. Here, the normal force. The normal force is given by which component of the weight, the x or the y component? The y component. And if I increase this angle right here, what happens to the y component of the weight? Does it go up or down? It does what now? Let me show you. So if I imagine I have an incline like this, my block is here, I have a y component and an x component of the weight. But if I make it steeper, like this, now I have a y component and an x component there. That x component gets bigger and the y component gets smaller. So here my normal force decreases, and over here my normal force is bigger. You'll follow me? All the way to the extreme when it's on a horizontal surface, and then the normal force is equal to the weight. Yeah, Jocelyn.
Does that mean, in regards to the previous question, if the block was pulled at an angle, the F time would have been less?
Right. So we had a previous problem where we had a block that's being pulled by a force in this direction like that. And she asked, would the normal force be less than the weight? Would it, y'all? The normal force be less than the weight in this case? Yes, it would be less than the weight. We talked about that like with the grocery cart at Walmart, right? You pull it, because when you pull it, you're decreasing the normal force because you're applying a force that goes up, and that causes your normal force to decrease. Okay? All right. Okay, and then I have a few questions for chapter 5. Because I don't think we did this at all, did we? Okay, we're just going to do a few of these questions. Remember, for chapter 5, there's very little. Well, there are five questions, I think, for chapter 5. But I'm going to ask you to calculate the work. Remember, that's just the force times the distance times the cosine of the angle. Be careful if there's any extra information that you don't get thrown off by that, okay? Just the force times the distance times the cosine of the angle. That's all you need to calculate the work. You'll need to know like the units of work or joules, the basic SI units, right? Newton meters or kilogram meters per second squared times meters. Y'all know how to find those basic SI units. And then you need to know how to determine if it's positive or negative work. If they're in the same direction, it's positive work. That is, if the force and the displacement are in the same direction, it's positive work. If they're in opposite directions, it's negative work. If they're perpendicular, it's what? No work at all. Right. That force is not doing any work. All right. Is it possible to do work on an object that remains at rest? Yes or no? I'm going to stop at 28. 28. Okay, right. No is the correct answer. Because remember, work is the product of our force and our displacement. If an object's at rest, that means its displacement is 0. And so there is no work being done on the object. A box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? No work, negative work, or positive work? Think about how your forces are drawn in this case. I'm going to stop at 42. 42. We're going to 45. Oh, very good. It does negative work because if you think about the forces, I have one force. This is just the force that you're pulling it with. And then I have the frictional force, this kinetic frictional force. We're moving at a constant speed in this direction. This force is doing negative work because it's opposite the direction of the displacement. This force is doing positive work. And actually we'll find in the next, on Friday and Monday of next week, we'll find that the actual total amount of work being done on this object is 0 because it has no net force. So when we add up all the works, it equals 0. But don't worry about that for now. The friction does a negative work. Can friction ever do positive work? Oh, I didn't tell you to do it, right? So the answer to this one is yes. So I know everybody's putting no, but put yes for this one. Okay? But let me tell you the answer for the previous one. What do you call Santa's helpers? First of all, I don't believe in Santa Claus. Right? I'm sorry if that crushes anybody. But what do you believe? What do you call Santa's helpers? You don't know. Subordinate clauses. I'm sorry, did I crush you with the whole Santa revelation? No, y'all know there's no Santa Claus. Subordinate clauses. Santa Claus, subordinate clauses, sub. All right. There's always a few, aren't there? Yeah. A was the right answer. It's really sort of a special case. Like, for example, if you have a box on the back of a pickup truck, in this case, the box moves along with the truck. So Actually, let me go back up so I can draw my pickup truck.
It'd be more fun to have a truck with no wheels doing it.
That would be cool. Yeah, so here I have a box. The displacement is in this direction. It's moving in this direction. So the box would tend to move off the back of the truck, right? So the frictional force is actually going to be in this direction. Because the frictional force always opposes the direction of motion, but the box would tend to move off the back of the truck by the law of inertia, and so the frictional force is actually in the same direction as the direction that the truck is moving. All right. How about this one? Baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? Say about the work done by the catcher on the ball. As the catcher exerts a force on the ball, what work is done by that force? Positive work, negative work, or zero work? All right, I'm going to stop. Oh, goodness. Okay, I'll stop at 55. 55. It is B is the right answer. B is the right answer. You think about this, right? There's this ball. It's moving in this direction, and the catcher, this is like the catcher's mitt, he exerts a force in this direction. So the force is in this direction, the displacement is in this direction, and so it stops it. Listen, we'll get to this a little bit later. We'll talk about the energy and what the negative work means, and this will make more sense to you. But just know that he's exerting a force that's opposite the direction of the displacement. So I think one or two more. I know we're going to skip this one.
Dear knows if there's
All right. The ball is being tied to a string. The quizzes are due tonight, right? Or no, tomorrow night. Yeah. So a ball is tied to a string and being whirled around in a circle. What can you say about the work done by tension? All right, what you want to ask yourself here is, what is the direction of the tension? So I have this ball on a string, it's going around in a circle like this. What is the direction of the displacement? Like, I can tell you the direction of the displacement. It's in this direction. The displacement is in that direction. What is the direction of the tension on this object? And then, what is the work that's being done? All right, very good. I'm going to stop at 1 minute. 1 minute. Ask your neighbor. Sure. Okay, very good. A is the right answer. Because here the tension, the rope is right here, right? So my tension is here. Later in chapter 7, I think we get into circular motion more, and we're going to revisit everything that we've done up to here. But the tension is along the string. So it does no work at all because the displacement and the tension are perpendicular to one another. You lift a book with your hand in such a way that it moves up at constant speed. While it is moving, what is the total work done on the book? Sorry, this gets into our next topic. But the answer here is 0, so just put D and then we'll call it quits here.
There's no acceleration.
So there's no net force. The net force is 0, so the net work that's being done on it is 0. But we're sort of mixing it up with what we have with energy. All right, I'll stop at 40. Hold on, let me just see what we got next.
Is that the first 10 of the day?
Huh?
Was that the first 100% of the day?
It was, yes. Yeah, so we're going to hold off on the kinetic energy for Friday. Chapter 5 is a lot easier. Am I right? Matt, what's up? Sure. You'll like chapter 5 a lot more. So work is zero when the displacement and the force are perpendicular. When they're perpendicular, they're at 90 degrees to one another. So, I mean, let's say, for example, our inclined plane, right? If we have an inclined plane, and I know that this object is, say, moving down the inclined plane, is moving down with a velocity in that direction. Let's say that it has a frictional force. The frictional force here is doing negative work. The x component of the weight is doing positive work, because those forces are either with or against the displacement. But the normal force, Fn, it's doing work none at all, because it is perpendicular to the displacement. Anytime your force is perpendicular to the displacement. And then also the force component, the weight in the y direction, this is also doing work equal to zero. Even though there's an actual force there, it's not doing any work because it's perpendicular to the displacement. Is that clear? Does that answer your question? Not really anything more complicated than that. I gave you a series of questions last time. Didn't we do this where I showed you the blocks with all the different forces on them? Yeah, so like if I had blocks with forces like this, these represent the forces. The displacement is in this direction, then I would have positive work. I would have zero work. I'd have negative work. Positive because they're in the same direction, zero because they're perpendicular, negative because they're opposite directions. That comes about from your cosine too, right? Cosine of 0 is 1, cosine of 90 is 0, cosine of 180 is negative 1. All right? I'll spend a little time reviewing for the exam. That's everything so those are all the loose ends that are tied up. But spend a little time now reviewing for the exam. Is that okay? You can look at old exam questions, work through some old things. If you need to go, understand, that's fine. I'm not offended. We might have a fire drill, so you might miss that, unfortunately. I don't know if we're having it in this class. They don't tell us. Okay? So as I've said before, our exam, I think it's 26 questions plus there's one extra credit problem. That extra credit problem is worth 3.8 points. So each question is worth 3.8. I think it's right around 3.8, 3.5 to 4 points for the extra credit. You'd be multiple choice. Listen, you'll have, let me just point out, on your form, you're going to get your form tomorrow, or you'll have little markers in the middle. I'm going to have a box here for you. This is for your scratch work. All right, so you keep your scratch work in that box, and then you'll also have another box down here for your extra credit, number 27. All right, so you'll get that, and you'll write your answer on the front of it. So please don't write outside of that box. It sort of messes up my software. Okay? You'll have Chapter 3B, all of Chapter 4, and then the first part of Chapter 5. I'll call it Chapter 5A. Chapter 3B is just projectile motion. I think there were 8-ish questions on projectile motion, a couple of calculations, problems that you'll probably expect to see, and then some questions about sort of the nature of projectile motion and how it works. In Chapter 4, it's all about Newton's laws. That's the big bulk of the test. So projectile motion, about 8 questions. I forget exactly, but right around that. Newton's laws is going to be about 12 questions or so. You'll have 1D problems where you have objects like the elevator problems that we worked. You'll have 2D problems like an inclined plane. You might have a couple of those. You'll have the thing where I give you all the equations for the inclined plane and I ask you to tell me which of these equations are correct or incorrect, that sort of business. You'll have friction problems. You'll have some basic stuff about Newton's laws. You might see some unit stuff there, like what's the unit of a Newton, the basic SI units. We'll come back to that. And then in Chapter 5a, it's just those basic things about work. That is positive, negative, and zero work. And then also just calculating work. The work done on an object by a force. Work equals FD cosine theta. You will have an equation sheet. You'll have that equation sheet from here on out. It really picks up with Chapter 5, and this is the only equation that's really relevant. But I'll just go ahead and give it to you so that you'll have it. I just printed it on the back of your form. So you start getting familiar with it for upcoming exams. Okay? Just to remind you, you really only have 4 equations, so if you're really big into memorizing equations, you have a pretty easy job. It's just our 2 kinematics equations, v equals v naught plus at, x equals v naught t plus 1/2 at squared. You have F equals ma, and then you have the frictional force is mu times the normal force. And that's really all we have as far as equations. But remember, we have special cases for these for projectile motion. Acceleration in the x direction is 0, so this goes away for our x components. And then we have this for both static and kinetic friction. You need to know what are the differences between those 2 types of friction. All right? Okay. You want to look at some old exam problems? All right, let me pull them up. Do I have them all here? While I'm pulling these up, you know, what did I make on my last paper? Did I tell y'all this? 100%. I was blown away by that. Aren't y'all blown away? Yes, thank you. And so I was very disappointed. I got another major term paper back. I was very, very disappointed to learn that I made a 95%. It's terrible. My wife was so disappointed. All right, so most of these are going to be exam 2s that you're looking at. Exam 2s. Sometimes you might be, not that one. Goodness. Let's see, let's look back at, this is fall 2012. Let's see what we can rustle up here. Okay, good projectile motion problem. You kick a soccer ball. This is fall 2012, problem number 4. You kick a soccer ball at an initial velocity of 20 meters per second at an angle of 30 degrees from the horizontal. It lands some distance away. How long does it take to come back from the ground to the ground? All right, so I always like to draw a picture. It always helps me to sort of remember my scenario. And this is the scenario that I have. Starts here, starts here. I know my velocity here is 20 meters per second. I know that this angle is 30 degrees, and that's all I know. But I want to know what is the time over here. Remember, I have to use that little trick that we did where I know that at the top of the trajectory, that v in the y direction is equal to 0. And so I say v at the top in the y direction is equal to v naught y plus ay times t. And then I have to find my x and y components. V naught y is equal to 20 sine 30. Which is 10. All right, so I have 0 equals 10 minus 10 meters per second squared. This is the initial velocity, 10 meters per second, times t. And I just solved that for t. And then I get the answer here, or I get this answer, is 1 second. And so I select B, right? No, very good. I select D, because that just gives me half the time, not the total time. And then, you know, there's any number of things I could ask from here, like what is the total range? the total range would just be Vx times t. That would be 20 cosine 30. I'm sorry, what now? Oh, you are. Yeah, bro. Okay, this is our initial velocity in the y direction. Our y component is right here. So usually on these problems, you're going to have to find both components. In this problem, you only needed one component, but usually you're going to need both of them. All right. I find the time at the top. The total time then is twice that. If I wanted to know the range of the problem, I would take the velocity in the x direction. That's the x component of E naught, 20 cosine 30, times the total time, which is 2 seconds. That's about 40 meters. Right, 20 times 0.86 times 2. Oh, it's 34 meters. So this would be for the total range. And then I could also find the y height as well. The y height, that is this y right here, would be equal to v naught y times t top. Remember, this is going to be 1 second plus 1/2 ay t squared. That's going to be 10 meters per second. That's v naught y right here, times 1 second plus 1/2 of -10 times 1 second squared. That's 10 minus 5 is 5 meters. So that was one of our basic projectile motion problems, but you could see one like that as well in the test. The other basic projectile motion problem that we had is one like you did in lab, where you just kick a thing off the side of the table, and then you calculate the time and the range and all that jazz, the velocities at different times. Okay, y'all might be able to do those really quickly in under a minute or two, okay? Yes, y'all can do that? Try to do it quickly. I don't want to rush you, like you certainly don't want to rush through it, but you can't stop and think too much. Any questions about this, y'all? Feel fairly comfortable with these projectile motion problems? Okay. All right. You'll probably see some questions like number 5 about just sort of what's true about projectile motion. In this case, we can look at these. The y component of the velocity doesn't change. That's not true, right? The y component of the velocity changes quite a bit. It goes up and gets small as it goes up, and it gets bigger in the negative direction as it comes down. The acceleration in the y direction is constant. True or not? True. That's true. It's not 0. It's -10 in the y direction. The acceleration in the y direction, that's not true, right? Because it's -10. The maximum height is dependent on the x component of the velocity. Is that true? Not true at all, in fact. Not dependent upon the x component of the velocity at all. The velocity of the object at the top of the trajectory is 0. Is that true? No. Very good. Not true. In fact, at the top of the trajectory, it's sort of true, but at the top of the trajectory, it does have a velocity, but it's only in the x direction. Now, we could make this a true statement. We could say the y component of the velocity at the top of the trajectory is 0, and that would be true. But as it's written, it's not a true statement. Be careful on those. Make sure you read the words carefully and think about what they're saying. But don't think too much. Just put the right answer. Okay. I want to do this other projectile motion problem. All right, a ball is rolled horizontally off a table with an initial speed of 0.24 meters per second. Stopwatch measures the ball's trajectory time to be 0.3 seconds. What is the height of the table? I got the time, so this is a pretty easy problem. I can draw a picture here, just to remind me of the scenario that I have. Recognizing that the velocity in the y direction, the initial velocity in the y direction here, is equal to 0, because I only have an x component to that velocity. And if I'm looking for the height of the table, that's going to be y. it's going to be v naught y times t plus 1/2 ay t squared. This term goes away because my velocity in the y direction is 0. And I just solved this for the height. 1/2 times -10 times t squared, that's 0.3 seconds squared. That's 5 times 0.09. A is the right answer, 0.44 meters.
You use 9.8.
I think I used 9.8 on this, yeah. So this, if you actually put this in your calculator, this should be 9.8.
And you're using 10 on the exam?
I'll use 10 on the exam, yeah. It just makes life easier for y'all a little bit. Slowly moving towards no calculators on the exam. Y'all would like that, right? That would be good?
Just don't make it a rule not to use it, and it's no problem.
Okay. I have to do it someday. Remember on this, your hang time for a projectile is always dependent upon the y motion. So A, even though it goes a shorter distance, is in the air for a longer time. Always the y motion dictates the hang time. You'll see some stuff about Newton's laws, like for example, if it's moving at a constant velocity, that means its net force is 0 or not 0? It's 0. If it's moving at a constant velocity, its net force is 0. In this case, D is the right answer. The net force is 0. Could see something like 12 here. Pretty simple problem where you have 2 ropes attached to a 40-kilogram object. Can y'all read that in the back? Oops, you can. Okay, 2 ropes are attached to a 40-kilogram object. The first rope applies 25 newtons, the second 40 newtons, but in the opposite directions. What is the resultant acceleration? So I have 40 newtons in one direction, 25 newtons. That means my net force here is 15 newtons. And so it's just simply F equals ma. That's 15 newtons equals 40 kilograms times the acceleration. And so 15 over 40, that's what? 3 over 8. E? What? E? E, right. 0.38 is the answer. 15 over 40 is 0.38. Okay? This is making you feel more comfortable? These are pretty straightforward, right? Let's look at some inclined plane problems, because you'll certainly have that. Yeah, this is a good one, too. This is a nice 2D problem. It's actually a little bit complicated, because I have this guy who's pulling up with a force on this block. I'm going to just draw all the vectors over here. I have the weight acting down at 200 newtons. I have a normal force, which I don't know what it is. It's not 200 newtons, right? I even said that here. I have the components of this force. I'll call this Fx. It's going to be 55 cosine of 35. And then I have Fy, which is going to be 55 sine of 35. Now I do know that the sum of the forces in the y direction is equal to 0, because this block is not accelerating in the y direction. So I can write the sum of the forces. That's 55 sine of 35 plus Fn minus 200 equals 0. So then I can find my normal force. And I get 170. Now listen, what we're really going for is the coefficient of kinetic friction. But one of those formulae that you just have to know is that Fk is equal to mu k times the normal force. So if I want to know that coefficient of kinetic friction, I need to know the normal force, and I need to know the kinetic friction. Now, a force that I haven't drawn on here yet is that force, which is the kinetic frictional force. It tells me that it's moving at a constant velocity. That means the acceleration equals 0. So I can say then that the sum of the forces in the x direction equals max, which is 0, and that's equal to fx minus fk, which is equal to 0. So fk then is equal to fx, which is 55 cosine of 35. All right, that's equal to 45 newtons. So then if I want to find my mu is just fk over fn, which is 45 over 170 so I get 0.267. Well, 0.265. I carried a sig somewhere differently, but 0.267 is the right answer. All right, that's a good test question. You could see something like that. It took me a few minutes to do that, but hopefully you can look at this and say, you can look and say, well, I know that my kinetic friction has to be the x component of this, and that my normal force is going to be something less than 200, this amount less than 200. So you might not go through all these steps on your test. You might be able to do a significant amount of that just sort of in your head. But if you have to write it out, that's fine. You should have enough time to do so. All right? Okay. Let's look at an inclined plane. You'll have a question like this where you're just looking for the equations. Well, I didn't have a good inclined plane problem here. Let's see. I'm going to do FO5 exam 1. Man, these are hard tests. Okay, I'm sorry. Let me do another one. We'll make this the last one. I know you're itching to go. All right, this is exam 2, FO7. Sorry, my computer's locked up. Oh. You see a problem like this with the elevator, y'all had a homework problem similar to that. Well, we just worked this problem. I'm sorry, do y'all want to do an inclined plane? You do? I think let me find another one. 8. Okay, so here I have this figure. This is Fall 08, exam 2, number 10. I have a block with a mass of 10 kilograms. It sits on an inclined plane with an angle of 30 degrees. What is the minimum force that the block remains in place? Listen, folks, hopefully you can look at this and just say, well, look, I know that this force is the x component of the weight, right? Can y'all look at that and see that? And that is equal to Fw cosine of 60. And so I can just say, well, force is equal to Fw cosine of 60, which is going to be 100 newtons times the cosine of 60, which is, that's 50, right? which is 50. All right. Now you might have to go through, if you're not quite to there, you might have to go through and draw your coordinate system, and then realize that your weight is here, and it has an x and a y component. So there's FWY. That's going to be FW sine of 60. And then this is your x component, FW cosine 60. All right. We only have a couple minutes left. Any other questions? We'll have a help session this afternoon. Yeah. Hold on, hold on. No, hold on just a second. So she has, and one of the problems is that F minus FW cosine 60 is equal to 0. That's only if it's not accelerating. So in this case, it sits. It says it sits there, so it's stationary. There you go. The acceleration in the x direction won't always be 0. In the y direction, it will always be 0, not in the x direction. All right, guys. Help session today at 3. I'll see you on this room.
I got the challenge for